This lecture is part of an online course of multivariable calculus, and we are going to look at the Lagrange multiplier method, and we're going to see how we can use that to optimize a function of 2 variables or 3 variables with a constraint. So let me start. The goal here is this. We want to maximize or minimize f of x and y with constraint g of x and y equals to c. So the method of Lagrange multiplier is this. We need to solve the equations this. Gradient of the function f that we want to maximize or minimize is equal to the lambda gradient of g, and also we need to look at where g is equal to c. What is lambda? Lambda is a scalar, okay, and it's called Lagrange multiplier. Lagrange multiplier. Okay, so after we find gradient of f and we set it equal to lambda gradient of our constraint, we have a system of equations like this, and after we find the system of equations with the variables lambda, x, and y, then we can find the optimum values for f. Now let's have observation and see why we have this equation in here. So observation, we say that let the point A and B minimizes or maximizes f subject to the constraint g of x and y equals to the constant c. And suppose that gradient of g at the point a and b is not equals to 0. Then we have gradient of f at the point a and b is equal to lambda gradient of g at the point A and B. The question is, why? Okay? So I'm going to answer that question. Let R of t be a parameterized curve on the surface g of xy equals to c, and at the time 0 it passes the optimal point, the point A and B. So basically we have a curve like that, R of t, and it's on g equals to c, and basically just at the point, for example here, at the time 0 it passes through the optimal point A and B. Okay, since A and B, the point A and B is optimal point, it means that it maximizes or minimizes f, then derivative with respect to t of f of R of t at the time t equals to 0, which is the time that the curve passes A and B, is equal to 0 because it's the optimal point. So derivative of the function at the optimal point is equal to 0. So what is this derivative? Using chain rule, this is basically gradient of f at a point A and B, basically at the time t equals to 0, times derivative of the inside function, which is r prime at 0. Okay, and this derivative is 0, which means what? Which means that gradient of f is perpendicular to r prime. Okay, so at this point, let's have r prime like that. Let me graph it in here. So this is r prime at 0, and then the gradient of f is just basically, this is gradient of f, is basically perpendicular to r prime, because this point A and B is optimal point, so the derivative would be 0. Using definition, I get that. Also, g of r of t is equal to c, right? That's equation of c for all, equation of g for all t. So now let's take derivative of that expression, d dt of g of r prime of t at the time t equals to 0 is equal to d dt of the right hand side of that. Okay, now let's look at this one. Derivative of a constant c is equal to 0, and derivative of g of rt based on the chain rule, it's what? It's gradient of g at the time 0, which is basically the point A and B, dot r prime at 0, right? And since this is 0, because the right hand side is 0, the dot product of these two vectors is 0, which means what? Which means that gradient of g is perpendicular to r prime. So I have gradient of g also in here to be perpendicular to r prime, or I can also graph gradient of g in here with a different different direction. And as you see, gradient of f and gradient of g, basically they are parallel to each other. That's why gradient of f is lambda gradient of g, just because these two are parallel. Okay, very good. So now using Lagrange multiplier, when I want to minimize or maximize a function f with variables x and y and with the constraint g of x and y equals to the constant c, when I want to solve that, I can write gradient of f is lambda gradient of g, and basically solve this system of equation. Partial derivative of f with respect to x is lambda partial derivative of g with respect to x. Partial derivative of f with respect to y is lambda partial derivative of g with respect to y. And g of x and y equals to c. And as you see, if I have this one, this is the optimization with two variables, x and y. Instead of this solving the optimization like that, I just need to find this to solve this system of equations with variables x, y, and lambda. So I replace an optimization problem with solving a system of equations. Okay, we can do it similarly for three variables. So similarly for three variables, we have this. If we want to maximize or basically minimize f of x, y, and z subject to the constraint g of x and y and z equals to the constant c, I can use Lagrange multiplier. Basically kind of the same reasoning. I can write gradient of f is the lambda gradient of g, and g of x, y, and z equals to the constant c. It's the constant c, and if I solve it with and solve for four variables x, y, z, and lambda, so we have the Lagrange multiplier method for also three variables. And the next video we're gonna look at one example to see how we can apply that.